Welcome you all. Today let us discuss about the first law of thermodynamics in engineering thermodynamics. The first law of thermodynamics can be applied to a cycle, to a system executing a cycle, for an open system and to a closed system. The first law of thermodynamics already we have dealt in our school standards, and is also known as law of conservation of energy. The law of conservation of energy, or the first law of thermodynamics, states that energy can be neither created nor can be destroyed, but can be converted from one form to another form. So we can't create any energy or we can't destroy, but we can transform one form of energy to another form of energy. Coming to thermodynamics, this first law holds good, that is, we are trying to convert heat into work. Heat into work. The unit of heat is joules. Similarly, the unit of work is also joules. Joules is nothing but Newton meter in case of work. And how we are going to transform this heat into work or work into heat lies with the first law of thermodynamics. For the entire globe, for the entire earth, the whole source of energy is from the sun. So this is the sun. This is our planet Earth. Our planet doesn't have any energy on its own. It receives all the energy from the sun, either in the form of heat or light. Either in the form of heat or light. And we try to convert this heat or light for our day-to-day work. Like, I want to go buy a automobile, a car or a two-wheeler. There, I want to have this energy, mechanical work. Or sometime in this room, it is fully air conditioned. Here the temperature of this room is lesser than the atmosphere. Say the room temperature here is 20 degree, whereas the atmospheric temperature is 30 degree. Now I want to maintain the heat, or I want to push away the heat from this room to maintain this room at a temperature lower than the surrounding, for which I have to supply mechanical work, which is converted in the form of electric energy and has been supplied. So here we are trying to convert the mechanical work into heat energy, or we are supplying mechanical work to remove the heat, to maintain the temperature of this room less than the atmosphere. So there is an interaction between heat and work. And this first law of thermodynamics says this energy can be neither created nor can be destroyed. So we are trying to convert the heat into work or work into heat. That is our idea. So for the entire globe, where the plants get their food or make their food by a principle called as a photosynthesis, that is getting light from the sun by means of the filament chlorophyll in them, they are able to produce their own food. The plants are able to produce their own food and they grow. And the animals and the humans eat the plants to grow themselves. So the whole source of energy for the human beings and the animals also is indirectly derived from the sun. Even if you have tide energy, that is because of the sun. If you have wind energy, that is also because of sun. Wind energy is caused because due to the difference in temperature. When there is a region at a very high temperature and there is a region at a very low temperature, it is low temperature, it is high temperature. Whenever it is high temperature, the density is lesser. Whenever low temperature, density is higher. So the air tries to move from the low temperature regions to the high temperature region, and this difference is more. Then it will try to form wind energy. It tries to form wind energy. In India, as of now, we are able to produce more than 7,500 megawatts of energy by wind energy. So indirectly if we see, all these forms of energy are derived from sun, either in the form of heat or light, and hence the law of conservation of energy also deals with how effectively you are going to convert the heat into work or work into heat. This is a general thing. But now let us go deeper into the same. Let us have a vessel which is completely adiabatic in nature, and I am going to have a stirrer. So let us have any working fluid. It may be water or some other fluid also. Even it can be incompressible as well as compressible. So I have a vessel which is fully insulated. So this dashed line indicates heat transfer cannot take place from the system or from the vessel to the surrounding. Let initially we assume the temperature of this system is at T1, which is same as that of atmospheric. Let us say today the atmospheric temperature is at 30 degrees Celsius, and this stirrer is going to get stirred with the help of a pulley arrangement which is connected to a weight. So let us say it is a weight. It is nothing but a pulley, and this is a stirrer. And let us make use of a thermometer. Let us make use of a thermometer which has the readings in it to measure. So this is nothing but a thermometer. Now we can say this system is a closed system because there is no mass transfer into the system, but there can be energy transfer. We already know what is a closed system. A closed system is a one in which we doesn't permit mass transfer, whereas work transfer is allowed. Work transfer or heat transfer is permitted. Both are nothing but combined known as energy transfer. So energy can be transferred either in the form of work or heat, but generally students used to think that energy transfer means only heat transfer. But along with that heat transfer, the students should feel work is also a form of energy transfer. This work transfer and the energy transfer are nothing but energy in transit. These two types are nothing but called as energy in transit. That is, they are boundary phenomena. What do you mean by boundary phenomenon? If I take a system, the heat should cross the boundary. Then only I can tell heat transfer has taken place. Otherwise, the work transfer should happen across the boundary. Let me take a piston cylinder assembly, which is an example of closed system. Now, if I want to transfer energy in the form of work, then this boundary should have to move. Then only I can tell this is a work transfer. So we can see that work transfer and heat transfer are nothing but the forms of energy transfer, and they are known as energy in transit, which means the energy transfer should take place or should be felt at the boundary. So the heat should transfer from the surrounding to the system via the boundary. Similarly, for the work transfer also, the work should be transferred across the boundary. So they are called as energy in transit. So let us come to our case. So let us have a closed system where the mass remains fixed. There is no mass transfer into the system or the surrounding. Here the system is nothing but the fluid contained in this vessel, and the surrounding is nothing but the atmosphere. And initially I am going to impart work transfer to the system. It's nothing but energy transfer. I am going to give the energy transfer in the form of work. For this, what I am going to do means I am going to move this weight up and down, and because of this pulley and this arrangement, the stirrer will get rotated. The stirrer will get rotated. So the work is transferred to the system by the movement of the weight up and down, which we can indicate in a XY diagram. So we let us indicate this process in a working diagram, in a XY diagram. So this is nothing but W1 to 2. So W1 to 2 is a path function which not only depends on the end points 1 and 2 but also the path in which it's traveling. So let us say it is Y and it's X. So when I am going to transfer the work, why is called work transfer? Because the stirrer is rotating. Whenever a body is moving or rotating, it indicates there is a work done, because work is nothing but a product of force and displacement. This displacement may be in the form of linear displacement or even it may be in the form of angular one. Here the movement is linear, whereas if we are going to come to the stirrer, it is going to be rotational. Since this stirrer is getting rotated, what will happen means the temperature of this water will rise. Why so? If this vessel is not insulated, the heat generated because of the rotational stirrer will be going to the atmosphere. But we made completely insulated or adiabatic, that is no heat transfer take place from the system to the surrounding. So the work transfer will make the system to rise its temperature. Let us say it increases from T1 to T2. Let us say it is some 35 degrees Celsius. So I have imported the work transfer by moving the weight up and down because of the stirrer rotates, and since it is insulated, it results in increase in temperature of T1 from 30 degrees Celsius to 35 degrees Celsius. Okay, yeah, fine. Let us use small T1 and T2 for temperature in degrees Celsius, and let us use capital T1 and capital T2 for temperatures in Kelvin. So let us change the capital T1 as small t1 and capital T2 as small t2 as the unit of temperature here, what I indicated as degrees Celsius. Okay. Now what we are going to do means, now after the temperature is 30 degrees Celsius, let us stop the movement of the weight, or we will stop the work transfer. Now the one more thing is, let us remove the insulation layer. Let us not allow, let us remove this insulation, so there will be heat transfer between the system and the surroundings. So what will happen now? Heat transfer from the system to the surrounding will take place, because the system temperature is now 35 degrees Celsius and the surrounding temperature is 30 degrees Celsius. So heat always will flow from a body at higher temperature to lower temperature. So it's an exothermic reaction, or heat is evolved, or heat has been dissipated from the system to the surroundings. Until what the heat will be transferred, until this temperature will see atmospheric temperature, say 30 degrees Celsius. So until then the heat transfer will take place from the system to the surroundings. So we will reach from, once again we reaches from 2 to 1 by shedding the heat. So the system tries to come back to its original state 1 by removing the heat. So it's a very good example where we try to convert the work transfer into heat transfer. Both are energy transfer only, but we try to convert one form of energy into another form of energy, which is nothing but first law of conservation of energy. But the thing is, we started from 1, we ended to 2. Once again we come back to 1, which means the system executes a cycle. Now this is known as the first law of thermodynamics applicable to a cycle. So here there is only one work transfer and only one heat transfer, but there will be cases where there are more number of work transfer and more number of heat transfer. As soon as the amount of heat dissipated increases with the amount of work transfer, that is, if more heat is transferred to the system, more amount of heat will be rejected from the system to come back to its original state. That is, they are directly proportional. So which can be indicated as summation of work transfer in a cycle should be proportional to summation of heat transfer in a cycle. So in order to remove this proportionality, I have to put a constant. It is nothing but called as J, joules equivalent of heat, or mechanical equivalent of heat. This J has a value of 1 in SI units. So generally the value of J is 1 when you are going to do the numericals with the SI units. It is nothing but the first law of thermodynamics applied to a cycle. Now the same can be written in, I hope now let us erase this diagram. The same can be written another way. Cyclic integral of dW will be equal to J into cyclic integral of dQ. Now the cycle is replaced by the notation circular sign, and better to put even a arrowhead to indicate it executes a process, and the summation is indicated by the integral sign. So the same thing we have given in another form, that is the summation of the work transfer should be equal to the summation of the heat transfer. There is no loss of energy. Otherwise, in simple terms I can tell if there are number of work interaction, say W1, W2, W3, W4 should be equal to the summation of heat transfer. If there is only two heat transfer also, or even 3, this should be balanced. So let us say a system executes a cycle which consists of 4 work transfer and 3 heat transfer, but the summation of work transfer should be equal to the summation of heat transfer. So this is nothing but the first law of thermodynamics applicable for a system executing a cycle. And these experiments are carried out initially by the scientist J.P. Joule during 1840s to 1849, and he changed the working fluid from water to oil to mercury, etc. And for whatever the case, he found that the heat transfer is direct proportional to the work transfer. There is more amount of heat should be dissipated when more amount of work has been transferred. So that is he has carried out a number of experiments. He even varied this liquid water with solid material and tried to impart the work transfer in the form of friction, and he tried to dissipate the heat. So he had done a number of experiments with the various working fluid and even with solids, and come to a conclusion that the amount of heat dissipated is directly proportional to the amount of work you have imparted to the system. And before this person J.P. Joule, they assumed that heat, they assume the heat as an invisible fluid which moves from a body at a higher calorie, to a body at lower calorie. So they felt that heat is a form of invisible fluid which moves from a body at higher calorie to lower calorie, and is known as caloric theory of heat. But this theory is no more now, because now we feel that heat is not a form of fluid, it is a form of energy which moves from a body at a higher temperature. Instead of higher calorie, higher energy, it is depends upon only temperature, higher temperature to lower temperature. So the heat will be traveling from a body at higher temperature to lower temperature. Even though this may have higher energy, say this body has 500 kilojoules, this body has only 100 kilojoules, or even we can tell 1000 kilojoules, and here let us say the body is at 200 degrees Celsius, this body is at 100 degrees Celsius. So this is usually I give to my students where the heat will be traveling. Now the calorie of this body is less, is only 500 kilojoule, whereas the calorie of this body is more. So as per calorie theory of heat, the heat should flow from the higher calorie to lower calorie, but that is obsolete. Now the heat will be only flowing from a body at a higher temperature to lower temperature. So the heat transfer takes place only from left to right as per the latest theory of our heat. Whereas the heat will not be flowing from this body, lower temperature body to higher temperature body. That is, the heat will travel from only body A to B because the body is at a higher temperature. Okay, so far what we have seen is nothing but the first law of thermodynamics applicable to a system which executes a cycle. Now let us move to apply this first law of thermodynamics applicable to a system which undergoes a process rather than a cycle. So this is over. This we made it, and we found that cyclic integral of dW will be equal to J into cyclic integral of dQ. Even if you want, you can put in here again. Now let us go and derive the first law of thermodynamics applicable to a closed system as well as to an open system. Let us instead take a closed system. Let us take a closed system. A closed system is one in which there is no mass transfer, but there is an energy transfer. The energy transfer may be in the form of heat or work or both. Okay, so this is a closed system. The closed system is nothing but mass is fixed or mass remains constant. The mass will not vary. Now I am going to give, but there is energy transfer. There will be energy transfer and there can be a energy transfer out. This energy may be in the form of heat or work or both. Let us take the example now. This energy transfer is in the form of heat. Let us assume I am going to supply, say, some 100 kilojoules of energy. This K should be small letter and J should be capital letter because J is the name of a scientist, Joules, and K is only kilo. So the letter K should be small letter and the letter J should be capital letter. Let us assume the energy is transferred to the system in the form of heat and I am going to supply 100 kilojoules. And because of this energy supply to the system, I am going to obtain the energy transfer in the form of work. Let us say we are getting some 30 kilojoules of work has been done. So what happens to the remaining 70 kilojoules? So I have supplied 100 kilojoules of energy in the form of heat to a closed system. Because of the substitution of the heat, I am able to derive, say for example, I am able to derive some 30 kilojoules of energy transfer in the form of work. What happens to the energy, the remaining 70 kilojoules of energy? So now we come to an idea that Q is not equal to W because Q is the 100 and W is only 30 kilojoules. So what happens to the remaining 70 kilojoules? Before that, let us take the system alone, closed system alone. This system has certain energy. Before even this heat is applied, the system has certain energy. That is E1. That is nothing but the energy of the system. After this heat is applied, the remaining 70 kg will be added with this E1. The remaining 70 kilojoule will be added to E1 and it form E2 and it will come to E2. The energy of the system increases from E1 to E2 by absorbing 70 kilojoules of energy. So our idea is to convert all the heat into work. I am supplying 100 kilojoules of heat. I expect 100 kilojoules of work, but it doesn't happen. Whereas the energy should be conserved, which means before I am going to supply the heat, the system has certain energy, say E1. After supplying the heat, this energy of the system increases by absorbing this 70 kilojoules of energy. So now I can tell that Q equal W plus delta E, where delta E is nothing but E2 minus E1. Okay, so this E2 minus E1 is nothing but your 70 kilojoules. Q is nothing but 100, W is nothing but 30. So I can tell this Q is 100 kilojoules, W is 30 kilojoules, and E2 minus E1 is nothing but 70 kilojoules. So once again, the first law of thermodynamics holds good. The energy is conserved. It is not being wasted or can be created. One form of energy is converted into work and delta E. The energy is conserved. So this is nothing but first law of thermodynamics applicable to a system. This delta E is called as change in energy of the system. This delta E is called as change in energy of the system. This change in energy can be in form of two forms. This change in energy delta E can be in the form of two forms. One is macro and another is micro. So what is macro? Which is visible, which is quantifiable, is one is macro. So here the change in energy may be in the form of change in kinetic energy, may be the change in the form of potential energy. So these energies are visible, are quantifiable, and which can be perceived by human senses. Is nothing but change in kinetic energy and change in potential energy. Whereas the change in energy may be in the form of internal energy also. The change in energy may be in the form of internal energy also. So now this delta E has two components. One is macro and micro. In the macro we have change in kinetic energy and change in potential energy. In the micro we have change in internal energy. So I can replace this delta E with Q equal W plus delta of kinetic energy plus delta of potential energy plus delta of internal energy. These two forms are called as macro. This is called as micro. For a closed system, generally there is no kinetic energy. As well as we assume the gravity effects are neglected, which means the potential energy is also zero because energy H is not affected by gravity, and hence these two terms will drop down to zero for a closed system. For a closed system, there is no kinetic energy, as well as we assume the effect of gravity is not considered. Then what will happen means the Q will become W plus change in internal energy. The internal energy is generally given by the letter U. So it is Q equal to W plus delta U. Now this Q equal to W plus delta U is known as first law of thermodynamics applicable to a closed system. Whereas Q equal to W plus delta E is nothing but the first law of thermodynamics applicable to an open system. Because in an open system there is a flow happening, so definitely there is a change in kinetic energy, and if a flow is going to happen in a direction opposite to the gravity, then the effect of gravity will also come into picture. Either against the gravity or along the gravity also, the effect of gravity will come into picture, and we can't neglect the changes in potential energy also. So finally I can conclude like this. The first law of thermodynamics is applicable to a cycle. For a system is nothing but cyclic integral of dW will be equal to J into cyclic integral of dQ, where J remains 1 for SI units. And the first law of thermodynamics applicable to an open system executing a process is nothing but Q equal to W plus delta E, where delta E is nothing but the change in energy of the system. The change in energy of the system may be in the form of kinetic energy, or may be in the form of potential energy, or may be in the form of internal energy. In case of closed system, this delta E, the macro energy becomes 0 because there is no flow, and hence the kinetic energy 0, and we assume the effect of gravity is neglected, and hence the Q will be equal to W plus delta U. So this is nothing but Q equal to W plus delta U. So hereafter, whenever we are going to mention the first law of thermodynamics applicable to a closed system, means we have to remember that Q equal to W plus delta U. Whenever we are going for a first law of thermodynamics applicable to an open system, Q will be equal to W plus delta E. And whenever you are going for a cycle, then you have to feel that cyclic integral of dW will be equal to cyclic integral of dQ. Okay, fine. And let us have the sign conventions. The heat supplied to the system is positive. The heat rejected by the system is negative. That means endothermic is positive, exothermic is negative. And the reverse holds good for work transfer. Work supplied to a system is negative. I do not give any work or power to the system. Whereas the power developed by the system is considered to be positive. So this sign convention should be very clear for solving the numbers. This is a general convention. We are just following what they have taken earlier. So for example, if I am going to take a compressor where I have to supply the power to the system, then only I can compress the gas. Then the power is negative. Whereas in case of turbine, the system will produce power, positive power or useful power. Then it is called as what? Positive work done. If you are going to supply heat, it is called as positive. Where the system is going to reject heat, it is called as negative. So based on this, let us make a small work. That is nothing but I am going to supply heat on Q1, supply heat Q2, there is a heat rejection Q3, there is once again a heat supplied Q4, and there are a number of work transfers, say W1 and W2 and W3 is there. And before supplying this heat transfer, let the energy be E1, and after the process completed, the energy be E2. So the delta E will be equal to E2 minus E1. Now what we can say, or how we can write the first law thermodynamics to the system is nothing but Q1 plus Q2 is minus Q3 because the heat has been rejected from the system or exothermic, so it's minus Q3, and plus Q4 because the heat is added. W1 is positive because work is produced by the system. W2 is also positive because work is being developed by the system. Plus W3 is negative because we are supplying the work or power, plus delta E. So you should be in a position to understand the sign convention. W3. Yeah, one more times of W4, it is a W3. Okay, so it's not W4, it's only W3. So there are two positive work interactions and one negative work interaction because work is being supplied to the system and delta is there. So we found the heat interaction and the work interaction and the sign convention. And what about this E1 and E2 or delta E? This is nothing but called as energy in storage. Whereas this heat and work are called, already we discussed what is heat and work. This is nothing but energy in transit. Energy in transit. Why it is called as energy in transit? Why is it called as energy in transit? Because the heat transfer take place or the energy transfer take place across the boundary, or we can feel that along the boundary. Similarly, the work transfer also can be felt along the boundary. Whereas this E2 minus E1 is nothing but energy storage which will not cross the boundary, and hence it is called as energy storage. And moreover, this delta E is a property. Delta E is a property which means is a point function, which means it depends upon only the end points and not on the path. Whereas energy in transit, heat and work, they are nothing but path function. What is meant by path function? Not only they depends upon the end points, but also on the path they travel. So it's nothing but path function. So you should know, out of Q equal W plus delta E, Q and W are path function, whereas delta E is point function. I hope you already know what is the difference between point function and path function. Let us try to prove that delta E is a property. So energy in storage, let us try to prove is a property. Property means what? Is a point function. So for example, if I have a curve like this, it is 1 and 2. It's an expansion process. SPV. Now what is a delta P or dP? Is nothing but P2 minus P1. What about delta V? Is nothing but V2 minus V1. They are perfect differential. I can just find the difference between V2 and V1. Similarly, for the pressure, I can find what is the difference between P2 and P1. So they are called as perfect differential or exact differential. Whereas, what is the work done when I am going to move from 1 to 2? Whether I can tell W2 minus W1 If I am going to tell like this, is wrong. Because the area under the PV diagram indicates the work transfer. So now this indicates my work transfer. The same thing I can reach from 1 to 2 along path, another path. Say let this be path A, that's a path B, and this be path A. Now, even though I am going to start from the same point 1, I am going to enter the same point 2, but my work transfer will be more, which is indicated by black cross shaded line. Which means the work transfer not only depends on the end points, but also depends on the path in which it travels, and hence the work transfer is a path function. Is said to be inexact differential or imperfect differential. So it should not be written as W2 minus W1, it should be written as W1 to 2, or it can be written as 1 W2 in suffix. Similarly, the heat transfer should also be indicated as Q1 to 2, which is nothing but Q1 to 2, and you should not write as Q2 minus Q1. This is wrong. Up to here it is right. Both these are right, whereas this is a wrong one. You should not write like this because heat transfer is also a path function. The area under the TS diagram, the area under the temperature entropy diagram indicates the heat transfer during a process. So now this area indicates me the heat transfer. So as usual, if I go to change the path from 1 to 2, from A to B, I may have a different heat transfer. So if I am going to have from 1 to 2 along another path B, then my heat transfer also changes, because the area under the TS diagram is nothing but my heat transfer. So we found that both this heat transfer and work transfer are path function, whereas the properties, I have taken the pressure and volume as I have taken the example of the properties of the pressure and volume, which is applicable to all the properties, even for temperature, even for entropy, their properties, they are point function. So let us now try to prove that the energy in storage delta E is a property, rather than a point function, which means I can write delta E as E2 minus E1, and there is no need to write this one as what? E1 to 2. This is wrong, whereas this is right. Or this is also wrong. These two things indicates a path function, whereas this indicates a point function, which means point function means the delta E should be a property. Now let us take a small derivation and try to prove that this energy in storage is a point function. So let me try to move from 1 to 2 along path A, and from 2 to 1 along a path B. Now what is the thing? AB executes a cycle. AB executes a cycle along the path 1, 2 and 2, 1. Whereas 1 to 2 is a process. Whereas 2 to 1 along B is also a process. And let us take the system tries to move from 2 to 1 along another path, say C. So how many cycles we have and how many processes we have here? How many cycles we have and how many processes we have?
3 processes and 3 cycles.
No, there's only 2 cycles. It starts from 1 and goes to 2 and come back to 1. This is called as one cycle.
Yes.
There's one cycle along AB and another cycle along A and is going along C. So we have 2 cycles. The first cycle is what is cycle? You should start from the same position and end in the same position by taking a different path. So it is, the first cycle is AB. What about second cycle?
AC.
The second cycle is AC. If there's some other cycle, BC is not a cycle because both are traveling the same path.
Path.
BC will not be executive cycle because they are both traveling in the same path. So it can't execute a cycle. Okay. So there are only two cycles. The one is along A and B and the other is along A and C. So there are two cycles. How many processes are there? How many processes are there? How many processes are there? What is the process? You should start at one place and insert another place. There is no need to come back to original state. There is nothing but a process. So how many processes are there?
3 processes.
3 processes are there. Because the A is nothing but is a process. It started from 1 to another path A, and B is another process. We start from 2 and insert 1. C is another process. It starts at 2 and insert 1. So we have totally 3 processes and 2 cycles. Now we are going to apply the first law of thermodynamics for a cycle as well as the first law of thermodynamics applicable to a process. Okay, fine. So what is the first law of thermodynamics applicable to a cycle? Summation of dW should be equal to summation of dQ. If you want, we can put in here. Summation of dW will be equal to summation of dQ. So let us take first cycle. First cycle is what? A, B. It starts from 1 along A and reaches 1 along path B. So the first cycle is AB. Now let us try to write the first law of thermodynamics applicable to this cycle AB. So can you tell what is the first law of thermodynamics for a cycle now? What is the summation of work interaction? Otherwise I will write like this also. Summation of W cycle is equal to summation of Q cycle. The summation of work transfer in a cycle should be equal to summation of heat transfer in a cycle. So now you can tell me what is the answer. It is nothing but WA plus WB is equal to
Q cycles.
Q what cycle?
QAB.
Q not AB, QA plus QB. That is how much amount of heat is transferred when you are going to move from 1 to 2. Otherwise, if you are want to tell like this also okay. W1 to 2 plus W2 to 1 is equal to what? Q1 to 2 plus Q2 to 1. That's the meaning. Got the logic? There won't be any delta E. There won't be any delta E if you are going to execute the first law of thermodynamics for a cycle. That is, all the work will be converted into heat. All the work will be converted into heat if you are going to apply for a cycle. That is, WA plus WB will be equal to QA plus QB. Let us say this is equation number 1. Let us say this is equation number 1. So, can you now tell me what the first law of thermodynamics applicable to the cycle, the second cycle, AC,
WA
WA, very good, WA
plus WC
plus WC
equal to QA
QA
plus QC
plus QC. That's it. QA plus QC. Very good. So we are able to write the first law of thermodynamics applicable to a cycle. Very simple. All the work will be converted into heat. Let us now try to write the first law of thermodynamics for a process. So how many processes are there? There are 3 processes, A, B and C. Along the path A, B and C. Okay. Now let us take for the process 1 to 2 along A. Can you tell me what is the first law of thermodynamics? Whether now delta E will come into picture or not. Now we are going to apply the first law of thermodynamics applicable to a process and not a cycle. So delta E will come into picture or not. What is the first law for a system executing a process? Q equal to either W equal to delta, W plus delta E or Q equal to what? W plus delta U. For an open system is Q equal to W plus delta E. For a closed system, Q equal to W plus delta U. Then delta E reduces to delta U. So for a process, definitely we will end up with the delta E. For a process, definitely we will end up with the delta E. Now, can you tell me for this process 1 to 2 along A, what is this formula? Yes, we can try. What is the first law of thermodynamics?
Q1 to 2.
Yeah, Q1 to 2. The Q1 to 2 is nothing but what? QA.
Yes.
What I told is right. It's nothing but Q1 to 2 But here we are calling as QA. Both Q1 2 as well as QA are same. Very good. Equal to
QB plus
QB. Where is QB?
WB.
W
W?
base
A only, not B.
plus delta H.
Plus delta E.
Process yes.
Yeah, along the path A plus delta
E.
EA. What is delta EA? E2 minus E1. So you should understand physically what is A. It's nothing but Q12 is nothing but equal to W12 plus delta EA. Delta EA is nothing but E2 minus E1. So it's nothing but for the process 1 to 2. Now I hope you will be more comfortable for the second process. For the process 2 to 1 along path B. Now we can try and tell me. Now we are going to move from 2 to 1 along B. Yeah.
QB.
Very good. What is QB? QB is nothing but Q 2 to 1. The meaning of QB is nothing but Q 2 to 1. Very good. Plus equal to
WB
WB. Yeah.
plus
Plus.
delta EB.
So what is delta EB here?
It's the difference between 1 and 2. 2 to 1, sir.
Is 2 to 1 or 1 to 2?
2 to 1, sir.
No, you are starting from 2
Yes.
and ending at 1.
Yes.
So what is the formula?
1 minus 2.
1 minus 2. The final state is 1. The initial state is 2. So it will be E1 minus E2.
Oh.
Okay, so it should be WB plus E1 minus E2 QB or Q1 2 to 1. It is W 2 to 1. Whereas here if I am coming, it is Q1 to 2 is equal to W1 to 2 plus E2 minus E1. Got it? We are writing the delta E, taking the final state minus the initial state. Here the final state is 1 and the initial state is 2. But nothing to worry about these letters, it is understandable. So you can simply go with QA equal to WA plus delta EA and QB equal to WD plus delta EB for the process 2 to 1. Now I hope you will be very familiar for the expression for the process 3 to 1. Can you tell me now? For the process, not 3 to 1, it's a 2 to 1 along path C. Along path C.
QC equal to
Very good. QC equal to
WC
WC
plus del EB.
del E
B. Del EC.
EC. What is del EC?
1 minus 2. Sir.
Yeah, it is E1 minus E2.
E2.
So we have 5 expressions now. 2 for the cycles and 3 for the process. So let us say this is equation number 3, this is equation number 4, this is equation number 5. So we have 5 expressions. Now let us play mathematically to prove it is nothing but a property rather than a path function. Yeah. Okay, we have now 5 expressions. 2 applicable for a cycle and 3 applicable for the process. Okay. Now let us take the first one. From the first one, I will write QA minus WA is equal to WB minus QB. I have reassembled. I have kept QA here itself. I brought this W that side, so it become minus equal to WB. I have taken the QB to the other side, so it become QB. So by rearranging one, I got this expression. This expression is obtained by rearranging one. Okay, I hope you can understand. Now I want to substitute this value from equation number 3. What is QA minus WA? QA minus WA will be equal to what? Delta EA, isn't it? So just from this expression, I am moving this WA to the left hand side. So delta EA is nothing but QA minus WA. So I can substitute this QA minus WA as what? Delta EA. From this one, what is WB minus? From the equation number 4, what is WB minus QB? It will be equal to minus delta EB, isn't it? So from this expression, what is WB minus QB is nothing but what? Minus delta EB. Now we want WB minus QB. Yeah, we have WB minus QB is nothing but minus delta EB. So let us say this is equation number 6. This is equation number 6. So I will repeat once again. From the equation number 1, I shuffled the terms such a way with A terms on one side and B terms on the other side for work and heat. So I obtained expression as QA minus WA equal to WB minus QB. So this is the expression. I want to replace these terms with the 3, 4 and 5. So I found that QA minus WA is nothing but delta EA from expression number 3, and I found WB minus QB is nothing but minus delta EB from equation number 4. And hence I substitute both these things, and I found delta EA equal to minus delta EB. What does it means? The delta EA will be equal to delta EB. Both are same. Both are positive. Both are not positive. Both have the same magnitude. But only the difference is the direction. Why so? Because we can recall that A is along 1 to T. 1 to 2 is along A. Whereas B is what? It is in the opposite direction. But they have the same endpoints. So the magnitude remains the same, but only the direction changes, and hence the negative sign indicates is opposite direction. So in engineering, don't worry about negative sign. The negative sign indicates only the direction. It's a vector quantity. Okay, fine. Now, let us do the same for this expression number 2. Now nothing but QA minus WA equal to, yeah, you can try.
QC.
No QC. I have taken QA minus, I have taken like this, QA minus WA equal to what? WC is there. I am taking this QC this side. So minus QC. So it is QA minus WA is nothing but equal to WC minus QC. Now we can tell what is QA minus WA. QA minus WA is nothing but delta EA. What about, let us take the last equation. From this equation, I hope we can erase the first and 2 now. There's no more need. So WC minus QC is equal to what? Minus
Delta E.
delta E. So what is this WC minus QC now? Minus
delta
E C. So now we consider 6 and 7. Now we consider 6 and 7. The left hand side are equal, so the right hand side should be equal, which implies minus delta EB is equal to what? Minus delta EC. So minus minus and get cancel away, which is nothing but delta EB equal to what? Delta EC. So what I am about to tell here is nothing but we finally ended with what? Delta EB equal to delta EC. Let us recall the diagram once again to make the concept very clear. It's nothing but I am going to move from 1 to 2 along A and 2 to B, 2 to 1 along either path B or 2 to 1 along path C. So we got, what we got is delta EB equal to delta EC. What it means? Whether you are going to travel along the path B or you are going to travel along the path C, your delta E remains same, which means it is independent of the path it travels. That depends upon only the endpoints, which means it's a point function. Which means it's a point function. And this value will be equal to what? Minus delta EA. Why? Because these two directions are in one direction, whereas A in the opposite direction. So we can easily understand that the energy storage is nothing but a point function rather than a path function, because we found that it's independent of the path which travels. So finally we come to a conclusion that out of Q equal to W plus delta E, these two are path function, where delta E is a point function. Or else I can tell this delta E is a what? Delta E is a property. Let us recall once again. I will have 1, I move to 2, I come to 1. Along another path same. Let me tell this is pressure, this is nothing but volume. Now, what is dP for the cycle? What is dP for the cycle? What is the change in pressure for the system executing a cycle?
P2 minus P1.
That's a process. P2 minus P1 is not a process. Now I am telling for cycle. What is cycle? The starting point and the end point should be the same. So what is dP? P2 minus P1 is a process.
V2.
P2 minus I am asking for a dP.
Okay.
It's not so difficult.
Cyclic integral.
Yeah. What I am asking, what is the formula for dP? Final minus initial. What is the final state here?
1.
1. What is the initial state?
1.
1. So what is the answer?
0.
0. For system executive cycle, the change in the value of the property will be 0. So dP will be equal to 0, dVV will be equal to 0. Similarly, what happens to dE or delta E? dE is nothing but delta P only. dP is nothing but what? Delta P. Similarly, what is the value of delta E for a cycle? For a cycle, what will be the delta E?
0.
0. Why? It's a zero cycle. The starting point is also 1. The ending point is also what?
1.
1. So it should be 0 for a cycle. So that will only be end up with what? Cycling integral of dq equal to what? Cycling integral of dw, there is no delta E. Because when the system is executing cycle, the starting point and end point will be same. So delta is also a property and hence this value will be equal to what? 0. That is the reason why we don't have delta E when we are going for a cyclic system executing a cycle. System executing a cycle. So I hope now it will be very clear with the first law of thermodynamics applicable to a system executing a cycle as well as the first law of thermodynamics applicable for a system undergoing for an open system as well as for a closed system, for a process. If there is any doubt, I am ready to answer you. So we proceed further for 10 more minutes. So let us try to proceed further for 10 more minutes to derive the first law of thermodynamics expression applicable to an open system. So let us now go for open system. So what is the first law of thermodynamics now? What is the formula? Q equal to
W plus
W plus
delta E.
very good, delta E. Now the change in energy may be in the form of kinetic energy or potential energy as well as in the form of internal energy. So this is nothing but an open system. Can you give me an example for an open system related to engineering application? Can you give me an example for an open system related to the engineering application? IC engines, very good. The very good example is IC engine. So we have, if I am going to take a petrol engine, then spark plug will be there. I have an inlet valve, I have an exhaust valve, and I have a pistons and assembly. I have bending rod and a crank with a crankshaft. So there is a induction of petrol and air during the section stroke. So mass transfer is taking place, and this mass will go away during the exhaust stroke. And this heat transfer is taking place because the spark is good and the highly compressed fuel air mixture get ignited and combustion take place. So heat transfer is taking place. As well as because of this heat transfer, it expands. So the piston also moves down. This is work transfer. So IC engine is a very good example where both mass transfer as well as energy transfer in the form of heat as well as work transfer take place. So that's a very good example. Yeah, you can consider this one. So the example of open system is IC engines. Let us take it. Whether it's petrol cycle or diesel cycle is a IC engine is an example of open system. Then what about turbine? What about turbine? What's a turbine? What's a turbine? You have to tell. So what's a turbine? So turbine is a device. What will do?
So increase the pressure.
No, increase the pressure is not turbine. Increase the pressure will be called as a compressor, otherwise a diffuser. Static it means it called as a diffuser, and total pressure will come to compressor. What is the turbine? Turbine is used to produce mechanical power. Turbine is used to produce mechanical power. Let us assume in case of thermal power plant, it is not assumption, it is true only. In case of thermal power plant, what will happen? You are going to heat the water to steam high pressure steam, as high temperature steam will come with more energy and will come and hit on the blades. So because of this heating, what will happen? The blades will start rotating. When the blades is rotating, the blades are attached to the shaft as a single body. So the shaft also tries to rotate, and hence mechanical power is produced. What we done actually now? We made a shaft to rotate. By forcing the steam, high pressure steam at high temperature on the blades. Because of this one, the blade starts to rotate at a higher RPM, and hence the shaft attached to this blades also rotates, just like your axial fan. So this shaft also will rotate. If this shaft is going to continue to rotate, and we are going to place magnets, North Pole and South Pole, by means of a permanent magnetic field, then the magnetic flux will be transferred from the North Pole to the South Pole, and this flux will be cut by this rotation of the shaft, and hence an EMF will be induced. So the mechanical work can be easily converted into electrical energy by means of a generator. This device is called what? A generator, according to the Faraday's law of electromagnetic induction. Whenever there is a change in the magnetic flux linked with a closed circuit, an EMF is induced, which will be there as long as there is a change in the flux. If there is no change in flux, there is no EMF. So we want to change the flux. For change the flux, we have to rotate this shaft. How this shaft is rotated? By blowing the hot steam at high pressure and temperature. That is the cause. So turbine is a device which is used to produce the mechanical power. Whether it is an open system or not? Yes, it is an open system. Why? Because mass transfer is taking place. As far as energy transfer in the form of work, mechanical work is being carried out, and hence it is called as what? A open system. It is called as an open system. So turbine is a very good example for open system. What about compressor? What is a compressor does? What is a compressor?
By means of mechanical energy, it's producing powers.
Is producing?
Uh,
Mechanical energy itself is power.
yes.
So what's our output?
To compress the air.
Yeah. To process the air or to compress the air. So the reverse of turbine is nothing but the compressor. Now the input is nothing but your mechanical work or the electrical work. Because mechanical work can be converted into electrical energy or electrical power. So the mechanical power and electrical power are on the same. What we are going to visualize. So we are going to give that is the input. What is the output you want? To increase the pressure. Generally, we used to go with the rotary compressor for higher pressure. So the compressor should be, the direction of the compressor should be opposite to the direction of the turbine. So you can see the air is getting reduced, which means it will compress. And we have a number of stages of the blades to compress it. For this blade to rotate, we have to supply energy. In the last case, because the high pressure steam is there, it will rotate the blade. Whereas in this case, we have to supply power to the shaft. We have to supply the electrical energy to the shaft. So the shaft will rotate. Because of that, the blades will rotate. When the blades are rotating, it will suck the air inside and leave the air at a high pressure. Say from 1 bar to 10 bar or 12 bar. Depends upon the number of stages what you want. Even up to 6 bar. According to the cases, it varies. So the compressor is a device to increase the pressure. Of the air by compressing it. But the input is what? You have to supply work. Ultimately, you want to rotate the shaft. It's nothing but mechanical work. Okay. So, turbine. What about W in case of turbine and W in case of compressor? In which one is positive and which one is negative? Turbine, the power is produced. Compressor power is supplied. So which is positive and which is negative?
Compressor negative.
Compressor is negative. Turbine is positive. So whenever power is developed, it's considered to be positive. Whenever power is supplied, it's called as negative. This is the convention we are following. Very good. So this is compressor. What is a blower? We have the blower in our FM lab, in turbo machine lab. So what's a blower?
To blow compressed air.
To blow air, but the compression will be very high.
Yes.
The atmospheric air will be having a pressure of 1 bar, whereas in case of your blower it will be hardly 1.1 bar to 1.15 or 1.2 bar. So the pressure will be very less, but it's somewhat pressurized. Pressure. We got it is not pressure, but the increase in pressure is not appreciable. It is slightly above atmospheric pressure. So blow air. Whether it's a work absorbing machine, or power absorbing machine, or a power producing machine.
Power absorbing.
Power absorbing machine. So W is positive or negative?
Negative.
Negative once again. What about fan? We are sitting below the fan. This is actual fan. Here also we are able to get the air,
Yes.
but the pressure not very much. Almost same, but it's a little more. It's negligible.
Power absorbing.
Once again, power absorbing. W is positive or negative?
Negative.
Negative. Okay. What about pump? What is a pump? So up to here it is positive. Here W is what? Negative. Let us now come to a pump. What is a pump? You have pump in your house
To suck water.
to suck from water from the underground and to transfer it to the water tank. Okay, so what is the pump?
Power absorbing machine.
Power absorbing. So if you have to consume power, we are putting the electrical switch in our house. So it's nothing but power absorbing machine. Very good. So W is what?
Negative.
Negative. What is the difference between pump and compressor? Or pump and compressor, fan, blower, etc.
So compressor is to use it is applicable for air.
Okay.
Pump is used for both air and liquids.
No, we told correctly partially, then we deviated. Compressor is applicable only for air.
Yes.
Okay. What about pump? Whether you are using pump for your air, for in your house, where you are using a pump for lifting the water.
Waters.
So you are calling this pump for incompressible fluid like water, oil, etc. And even for blood is non-nutrient fluid. Whereas we are using the compressor blower fan, they are compressible fluid because they can use air or any gas. So if we are going to use any fluid, working fluid, which is compressible in nature, it is called as what? Your compressor fan and blower. Whereas the pump is a mechanism where we are going to supply incompressible fluid. Here also the pressure will rise, but the volume will not decrease. Here the pressure will rise, the volume will decrease. So that is the difference between the compressible fluid and incompressible fluid. Okay, that is pump. Very good. So let us now come to another application. I hope you may know what is meant by nozzle. Do you know what is meant by nozzle? Okay, what is a nozzle? Convergent nozzle. So what will happen?
It increases the velocity.
What will do?
It increases the velocity.
Very good. It is used to increase the velocity here. It is used to increase the velocity here. Let us use the letter C1 for inlet velocity and C2 for exit velocity. As already we use small v for specific volume. V1 and V2 for specific volume. So let us not confuse with the same letter for velocity. Let us use the letter C for velocity. So C1 is nothing but the velocity at section 1-1. C2 is nothing but the velocity at the section 2-2. The aim of the nozzle is to increase C2. So C2 should be greater than what? C1. This is the use of a nozzle. This is the use of a nozzle. So very good. So it is the kinetic head of any working fluid. What is a diffuser? Let us take a diffuser. What is a diffuser?
Increase the pressure.
Very good, very good. So the use of a diffuser is used to increase the pressure. So now it will become, the shape will be opposite to that of the nozzle. The shape will be opposite to that of the nozzle. So let us say the pressure is P1 here, the pressure is P2 here. Then P2 should be more than what? P1. Whether in a nozzle you have any rotating device?
Yes.
No. So whether there will be any work transfer?
No, sir.
No. Similarly, in case of diffuser, whether you have any rotating mechanism?
No, sir.
No. So there will be any work transfer?
No, sir.
No. So there is no work transfer in case of nozzle and diffuser. Whereas in case of turbine, compressor, blower, fan, pump, all these devices have some rotating devices or rotating blades. So they involve work transfer. But there is no need of any work transfer for the nozzle and the diffuser. There will not be any work transfer in case of nozzle and diffuser. And let us try to go with the last example. There are a number of applications, but we limit ourselves to the last application, namely throttle valve. Throttle valve or expansion device. See, expansion device. expansion device. All engineering applications are open system in nature. All engineering devices are open system in nature. Let us now take the throttle valve. So let us have the upstream section is 1 the downstream is 2. I am going to have some fluid and I am going to have a closed one. And what I am going to do means I am going to have a small opening. So what will happen to this fluid? The fluid will try to escape through this small opening. This is obvious. So I already had some fluid. It is already in compressor down way also, but I closed it. What I want to do it, I am going to let this fluid through go away or ready to open by a small opening or an orifice. Now, what will happen means the temperature of this fluid will drop due to expansion. This effect is nothing but Joule-Thomson effect. Joule-Thomson effect. Okay, so the temperature of this will drop. Instead of an opening or an orifice, even we can use a porous media. What is a porous media? What is a very good example for a porous media? A sponge. If you are going to put over water, it will suck the water because but you will not see the holes in that, but it's very, very small. So the porous media is nothing but an element which have minute holes or pores through which the air or any fluid can pass through it, but at a very low velocity. But the effect of this may be utilized for cooling purpose, just like in a throttle valve in a refrigerator. So the refrigerator consists of two things. One is the evaporator and the expander. Here it comes the compressor and the condenser. So this compressor, this condenser, this is expander or throttle valve. This is nothing but your evaporator. So this expander or throttle valve is nothing but the fluid will try to expand here. So its temperature will come down. So it will be able to pick up more amount of heat from the working medium. Okay. So that is where we found the effect of this one. Now this throttle valve or the expansion device is a device where the fluid is trying to escape through a small opening and orifice and the temperature may come down. But ultimately, during this process, what the physics happening is the enthalpy remains constant. There is no change in enthalpy. The enthalpy at inlet will be equal to the enthalpy at exit. So what is the use of a nozzle? To increase the velocity. What is the use of the diffuser? To increase the pressure. Similarly, what is the use of a throttle valve? The enthalpy remains constant. We have to feel like that. The enthalpy at the inlet should be equal to the enthalpy at exit. Instead of that, I can use capital H1 is also equal to H2. When the mass of the working fluid is 1, then capital H1 will become small h1. When the mass is 1, the capital H2 becomes what? Small h2 is specific enthalpy. It is kilojoule per kilogram. It's only kilojoules. It's only kilojoules. So we have seen a number of applications where the open system come into pictures. And all the engineering applications almost are only open system in nature. So the first law of thermodynamics mainly Q equal to W plus delta E is valid for most of our engineering devices. Let us take one by one, or let us derive this equation and we will try to apply for each and every device. Let us have a common thing first of all. So let us the upstream and the downstream. The pressure at inlet is P1, the pressure at exit is P2. The specific volume at inlet is V1. What is specific volume? What is specific volume? Volume per unit mass. Volume per unit mass. So what is the unit? It is meter cube per kilogram. Instead of meter cube, it is called as what? Meter cube per kilogram because the volume occupied per unit mass. So it is V1. Let the velocity at inlet be C1. Let the temperature at inlet in Kelvin be T1. Whenever I am using capital T, it is temperature in Kelvin, and whenever I am using small t, it is temperature in degree Celsius. Similarly, let us say the specific volume at exit is V2, the temperature at exit is T2 in Kelvin, and the velocity at exit is c2. Okay, so let us have any working fluid. For example, I am taking water. Now there is a continuous inlet flow happening inside, and the flow is also going to happen leave outside. And let us assume the flow is not varying with respect to the time as well as with respect to space. The flow is not going to vary with respect to time as well as with respect to space, which means the level of this water or any fluid inside the tank remains constant. Inside this tank remains constant. How much amount of fluid comes, the same amount of fluid will leave, and hence it is not varying with respect to time as well as it is not varying with respect to space, and hence it is called as steady state, steady flow energy equation. Steady state, which means it doesn't vary with respect to time. Steady flow, which means it's similar to a uniform flow. There is no change in flow with respect to the space energy equation. And generally, thermodynamics doesn't deal with the transient mode. It's always deals with steady mode. Even though we are studying thermodynamics, but we are going to study at the phases happening at equilibrium, and hence generally it is called as steady flow energy equation. There is no need to mention it is steady state, steady flow. It's sufficient to tell us steady flow energy equation because the thermodynamics fully deals with the system at equilibrium rather than the rate at which it is happening. That will be dealt with the heat transfer. Okay, fine. Now, out of these quantities, pressure, temperature, velocity, these three are intensive properties, which means those values will not vary with respect to mass. Those values will not vary with respect to mass. For example, this room, the pressure is 1 atmosphere. If I am going to make this room into two halves and I am going to measure the pressure, still the pressure will be what? 1 atmosphere. Okay, this room temperature is now how much? Say 22 degrees Celsius. If I am making this room into two halves, then also I am going to measure the temperature. Then also will be what? 22 degrees Celsius. Which means these properties doesn't vary with respect to the mass. Whereas volume will vary with respect to mass. If you have a small room, I have small mass. If you have a bigger one, I can accommodate more amount of mass. So the volume is an extensive property. So extensive properties are those properties which vary with respect to mass. Intensive properties are those properties which doesn't vary with respect to mass. So those things already you might be knowing, just we are recalling it. So these are the things. And let us say from a common datum, let the height be Z1, this height be Z2, this height be Z2. So these are the various properties. And what is the change in energy? It will be in form of what? The change in energy will be in form of?
Kinetic energy.
Very good. Kinetic energy, then
Potential energy.
potential energy, very good. Plus internal energy, very good. So internal energy you can designate by the letter U. Okay, so delta U. Now, this W for a closed system is nothing called as the displacement work. What is the displacement work? When a turbine is rotating. When a turbine is rotating, it is displaced. So it is called as a compressor has been rotating. Displacement work. So W means displacement work in case of closed system, but we are dealing with open system. So there should be some work when the fluid is moving from station 1 to 2. The movement of fluid itself is a work, isn't it? So that work is called as flow work. That work is called as what? Flow work, which is given by the formula PV. This is given by the formula PV, where P is nothing but the pressure at the particular cross-sectional area, and V is nothing but its corresponding specific volume. So now the change in flow work will be equal to P2 V2 minus P1 V1. Whereas in case of closed system, we have displacement work. That work is given by the formula integral of PdV. This and this are not the same. This is the energy which the fluid has to move from position 1 to 2. So the flow work is given by the difference of PV. So P2 V2 minus P1. Okay, so you should know that along the displacement work, we have the flow work also. Along the displacement work, we will have a flow work also. So the W have two types of W. One is displacement work, and the second is flow work. Okay. Now let us come to the formula. Q equal to the displacement work. I am going to give W only. What about flow work? It is P2 V2 minus V1 V1. What about changing kinetic energy? What is the formula for kinetic energy? What is the formula for kinetic energy?
Half mv square.
Half mv squared. But here we are not using V. Instead of that we are using C squared. Because we already are using the term V for specific value. So we are going to use the letter C for velocity. So the formula for the changing kinetic energy will be equal to half mc2 squared minus half mc1 squared. Plus, what is the formula for potential energy? What is the formula for potential energy? It is mgh. Okay, but here it is mg into h2 minus mg into h1 plus change in internal energy. So this is nothing but what? Change in potential energy. This is nothing but what? This term is nothing but change in kinetic energy. This term leads to your flow work. And this is nothing but your displacement work. So mg into h2 minus h1 plus u2 minus u1 plus u2 minus change in energy is nothing but u2 minus u1. Okay, fine. I shall let it be. I will take this space. So now what is happening is Q equal to W plus P2 V2 minus P1 V1 plus from these two terms I can take half EMS constant into C2 squared minus C1 squared. In the next two terms I can have it is what G into M into J into H2 minus H1. And the last term it is M into small u2 minus small u1. If I am using capital U2 minus u1, there is no need to put M. Whereas if I am going to use small u2, then I have to put M into u2 minus M into u1. So it is M2 into u2 minus u1. Either you can use calculator, then there is no need to put M. Because already I told, capital H is nothing but a part of M into small h. Similarly, capital U is nothing but a part of M into small u. Okay, so here I have written M into u2 minus M into u1. So here also I am taking, it's not m2, it is M into u2 minus u1. So let us assume that the flow of the fluid will be 1 kilogram. Let us assume the flow of fluid to be 1 kilogram, which means mass is 1. It means mass is 1. So the above expression will drop down to P2 V2 plus P1 V1 plus half into M becomes 1. So half into C2 squared minus C1 squared plus G into, here instead of H2 I can replace with Z2 because the condition what I follow is Z1 and Z2. So there is no need to put H, instead of that you can put Z2. Both are same. If you are not convenient with Z, you can even put H2, nothing wrong in that. So Z in G is Z2 minus Z1 plus M is also 1 plus small u2 minus small u1. Plus small u2 minus small u1. So let us take the terms which are having negative side to the other side so that it becomes positive. So minus u1 is there. If I want to take it to the other side, it becomes plus u1. So it is not plus here, it is minus. I am sorry. So it is u1 minus p1 v1 will become plus p1 v1. This minus half c1 squared will become plus half c1 squared. This minus g0 will become plus g0 plus already existing term q is equal to u2 plus p2 v2 plus half c2 squared plus g z2 plus w. So this equation is called as S of EE. S of EE stands for steady flow energy equation. So we found that we have taken all the terms which is negative side to one side and positive side we written there itself. So the entire thing become positive now. So what is u1 plus p1 v1? What is u1 plus p1 v1? Is nothing but h1 because we know that h equal to u plus pv, which means h1 will be equal to u1 plus p1 v1. So it's h1. So these two terms will become H1 plus half C1 square plus G into Z1 plus Q is equal to H2 plus half C2 square plus G Z2 plus W. Both are one and same. Both are one and same. So this also called as what? Steady flow implication. In the next section, in the next class, we will try to deduce this formula for various applications like turbine, compressors, fan, blowers, pumps, and nozzle, diffusers, as a throttle valve, and other engineering applications. Thank you.